Everyone thinks Tesla is losing the EV war. Chinese giants are cutting prices every quarter, opening new gigafactories and flooding global markets with batteries that cost a fraction of what Western automakers pay. That's the narrative you've heard 100 times. But that narrative might already be outdated, because while every automaker on Earth raced to win the exact same fight, bigger batteries, cheaper cells, more range per dollar, Tesla quietly stopped competing on that battlefield altogether. They didn't build a bigger pack. They didn't chase a cheaper chemistry. Instead, they went after a mechanical bottleneck buried inside the motor itself, one that's been quietly limiting every EV on the road, including Tesla's own cars, for over a decade. And once you understand what they actually fixed, you'll see why the EV war might be shifting away from batteries completely into a fight almost no Chinese automaker is currently built to win. So let's start with the trap every automaker, Tesla included, fell into first.
The battery trap. Rewind to the early 2000s. Electric cars were a punchline, slow, short-range, glorified golf carts that couldn't handle anything beyond a short commute. Nobody in the mainstream auto industry took them seriously. Then the Tesla Roadster showed up in 2008, and a few years later the Model S landed, and suddenly the conversation flipped. These weren't underpowered curiosities anymore. They were beating gasoline supercars off the line. That moment set off a global scramble to dominate the EV supply chain, and China moved faster and more aggressively than anyone. Chinese manufacturers locked down the raw materials that matter most, lithium, nickel, and cobalt, and built a near-total monopoly across the mining and refining stages most Western companies never bothered to secure. On top of that, they mastered lithium iron phosphate chemistry, a battery formula that's cheaper, safer, and easier to scale than the nickel-heavy chemistries Western automakers leaned on for years. The result was a strategy built almost entirely around one idea: bigger packs, lower prices, win through sheer scale. And for years it worked. Chinese EV makers could undercut nearly anyone on price, while still offering competitive range because their battery costs were structurally lower than everyone else's. But bigger batteries come with a hidden tax that rarely makes it into the marketing slides. Every additional cell adds curb weight, and that weight cascades through the vehicle. Heavier brakes to stop safely, a reinforced chassis to handle the mass, stiffer suspension just to keep it controlled. None of that is free, and none of it shows up as a headline spec. Here's the part almost nobody outside the engineering world talks about. A battery pack by itself is just a storage tank. It doesn't move the car. If the motor sitting between that battery and the wheels can't convert chemical energy into mechanical force efficiently, a huge portion of that expensive, hard-won battery capacity gets thrown away as waste heat before it ever reaches the pavement. The battery war was quietly running into diminishing returns, and almost nobody outside Tesla's engineering team seemed to notice or care.
The mechanical wall. To understand what Tesla actually solved, you first need to understand how an electric motor works, because this is where the real bottleneck was hiding the whole time. Every electric motor has two main components. There's the stator, the stationary outer ring that generates a rotating electromagnetic field, and there's the rotor, the central spinning core that gets dragged along by that magnetic field and sends torque out to the wheels. For decades, the standard approach has been to build that rotor from stacked silicon steel laminations wrapped in copper windings. It's a design that's cheap to manufacture, easy to mass produce, and has been refined for generations, which is exactly why almost every automaker still uses some version of it. The problem only shows up when you push RPM higher. As rotational speed climbs, centrifugal force starts pulling outward on every single gram of material packed inside that rotor with tremendous and constantly increasing intensity. At extreme speeds, the copper windings and steel laminations begin to experience real mechanical stress, microscopic stretching, tiny shifts in geometry, enough to throw the entire rotor assembly out of balance. That imbalance doesn't sit there quietly. It triggers a chain reaction. Vibration spikes, acoustic harshness increases, friction climbs as components rub against tolerances they were never designed to operate near. All of that generates heat fast, inside a rotor core with almost nowhere to dissipate it. Once temperatures climb high enough, the motor's inverter and control software have no choice but to step in and cut power output, because the alternative is catastrophic structural failure. This is why automakers have historically been trapped in a brutal trade-off. Push for higher RPM and you get blistering top-end acceleration, but you risk destabilizing the rotor and triggering thermal throttling exactly when you need power the most. Keep RPM conservative and you protect structural integrity, but you leave real performance sitting on the table. Nobody had found a way to have both, until Tesla did. Tesla's 2.5mm solution. Instead of reinforcing the rotor with heavier metal retainers or thicker alloy sleeves, the obvious brute force fix everyone else defaulted to, Tesla wrapped it in a precision-engineered carbon fiber sleeve. And the material choice alone tells you how deliberate this was. Carbon fiber delivers a tensile strength of roughly 2,400 megapascals, dramatically outperforming even the highest-grade automotive steels, while adding almost zero additional rotational inertia to the assembly. Here's the genuinely clever part of the design. That sleeve is just 2.5 millimeters thick, but it isn't simply wrapped around the rotor and left to sit passively. It's applied under carefully calculated tension during fabrication, which means from the very moment it's manufactured, it's already exerting continuous, controlled inward pressure on the rotor structure. So when the rotor spins up toward its design ceiling of 22,000 RPM, the outward centrifugal force trying to tear it apart runs directly into that preloaded inward tension from the carbon wrap, and the two forces essentially cancel each other out in real time. The rotor doesn't deform, doesn't stretch, doesn't drift out of balance the way a conventional design would at those speeds. The real-world payoff is what actually matters to the driver. The rotor stays microscopically stable and perfectly balanced even under sustained full load. That translates into repeated, uncompromised launches instead of one strong pull followed by a fade. It means sustained highway overtakes without the power gradually dropping off behind the scenes. There's no creeping thermal throttling quietly clawing back performance the way there is in a conventional rotor design. The car simply keeps delivering what it promised, lap after lap, mile after mile. The efficiency moat. This is where the story stops being about performance bragging rights and turns into a genuine economic weapon. Electric motors were already efficient machines, but at the extreme end of the RPM range, that efficiency used to fall off because heat and vibration forced the motor to back away from its peak. Tesla's carbon sleeve closes that gap, keeping the motor near its efficient sweet spot even under sustained high RPM load. But the real prize isn't a few extra percentage points of range, it's power density. Because the rotor no longer needs thick metal retainers to survive 22,000 RPM, Tesla can extract the same torque output from a motor that's meaningfully smaller and lighter than a conventional design would require. And that single change reshapes the entire vehicle's engineering math. A lighter motor means less overall drivetrain mass, reduced structural load feeding back into the chassis, and less heat that the battery's cooling system has to manage during hard, sustained acceleration. Every kilogram Tesla removes from the drivetrain is a kilogram it can either cut from the car's total weight or reallocate somewhere that actually improves the driving experience. That's not a headline-grabbing battery discount. It's something more durable, a structural advantage sitting inside the drivetrain itself, one that a rival can't simply erase by discounting battery cells.
China's edge was built entirely around the cost of chemistry. Tesla just proved the fight doesn't have to stay there.
The factory secret. Tesla has a well-documented history of open sourcing its patents, going all the way back to 2014. And Chinese automakers haven't ignored high RPM motor designs either. Xiaomi and BYD's Yangwang division have both pushed development into similar territory. So the real question isn't whether a competitor can build a high RPM motor at all. It's whether they can build millions of them identically at a cost that still makes sense on a sticker price. A patent hands you the blueprint, not the kitchen it was cooked in. Think of it like getting the printed recipe from a 3-Michelin-star restaurant. Knowing every ingredient and every step in the method doesn't come close to letting you replicate that exact dish at that exact quality level thousands of nights without a single mistake. That kind of consistency requires the precise equipment, the exact calibration, the trained hands and instincts built up over years, none of which shows up anywhere on a printed page. Wrapping carbon fiber around a multi-component rotor at the tolerances this design demands means operating within sub-micrometer precision, less than 1/1000th of a millimeter of acceptable deviation. Achieving that consistently requires advanced robotic winding systems that constantly monitor and adjust fiber tension, winding angle, and ambient curing temperature in real time, all governed by closed-loop AI control algorithms running continuous feedback corrections.
The stakes for getting it wrong are severe. A minor deviation in fiber tension or a single undetectable microvoid inside the carbon weave can cause catastrophic rotor failure once it hits 22,000 RPM. That's why every unit has to pass through high-speed automated laser inspection, scanning every square millimeter of the rotor surface for microfractures before it's ever allowed into final assembly. Building one flawless prototype motor inside a controlled R&D lab is genuinely achievable for almost any serious engineering team with enough time and budget, and competitors have already proven they can get a lab sample spinning at similar speeds. Maintaining a 99% plus commercial yield rate across millions of mass-produced vehicles year after year without that quality slipping and without the cost ballooning past what a mainstream buyer will pay is an entirely different category of problem. That's the real moat here. It was never about who can prove the concept works. It's about who can turn it into a repeatable, low-cost factory process. And that takes years of proprietary automation know-how that simply cannot be purchased off a shelf.
The real endgame. Right now, this motor lives in the Model S Plaid, where sustained high RPM is the whole point. But the manufacturing process behind it, tension-wound carbon, closed-loop precision that keeps a rotor stable under repeated stress, is exactly the durability engineering Tesla will want in its dedicated Robotaxi fleet. A Robotaxi isn't chasing 22,000 RPM in city traffic, but it faces something almost as demanding: thousands of accel and decel cycles a day for years without a maintenance bay ever touching the drivetrain. That's a durability problem, not a top speed problem. The same manufacturing discipline applied to a different part of the curve. Step back far enough, and the EV race has quietly moved past its opening chapter. For years, the working assumption across the entire industry was that whoever built the biggest, cheapest battery pack would ultimately win the war. That assumption still matters. Battery cost and chemistry aren't going anywhere, but it's no longer sufficient on its own to guarantee long-term supremacy. Brute force scale and cheap cell chemistry buy you a real but temporary competitive buffer. Long-term automotive supremacy is going to belong to whoever masters micro-precision manufacturing, thermal management, and extreme energy conversion efficiency, the unglamorous, invisible engineering happening on the factory floor, not the flashy battery chemistry announcements that make headlines. Tesla's carbon sleeve motor proves that the next real technological moat in this industry isn't being built in a battery lab at all. It's being built on an assembly line, one sub-micrometer wind at a time.
So here's the question genuinely worth arguing about. Does BYD, or any Chinese automaker with enough resources and enough time, have a realistic path to eventually breaking through this kind of automated manufacturing wall? Or has Tesla just permanently rewritten the rules of the EV powertrain game in a way that raw scale alone can never answer? If this breakdown actually changed how you see the EV race, hit subscribe because we're going much deeper into the engineering battles nobody else on this platform is covering in this kind of detail. Now drop your take down in the comments. Can China's manufacturing scale eventually crack Tesla's precision moat, or is raw scale no longer enough to win a fight that's shifted to the factory floor? And if you want to see exactly how China's planning to answer back, our next video breaks down the battery technology they're betting everything on to try and close this gap. You're not going to want to miss it.